Hello all, welcome to my channel. In this video, I will explain how to use simplex method to solve a linear programming problem when one of the decision variable have lower bound. So here we have maximize z is equal to 10x1 plus 6x2 plus 11x3. It is objective function which is as usual subjected to the first constraint 4x1 plus 6x2 plus 7x3 is less than or equal to 210. Nothing different in this as compared to earlier sums. 9x1 plus x2 plus 5x3 is less than or equal to 190. Again, no change. And the third constraint is 13x2 plus 2x3 is less than or equal to 175. So if we read the problem for objective function and for the constraints, we have found no change. But the change is here in the non-negativity restrictions. Here it says x1 and x2 both are greater than or equal to 0. And we have seen that x3 is also greater than or equal to 0. But here x3 is not greater than or equal to 0. It is greater than or equal to 1. Whereas x3 is not greater than or equal to 0, but its values is greater than or equal to 1. It means that x3 is not equal to 0. So this is a lower bound in terms of x3 value. So let us see how to solve such problems. So the step 1 will be equal to put x3 is equal to x4 plus 1. So everywhere we will replace x3 as x4 plus 1 and we get maximize z is equal to 10x1 plus 6x2 plus instead of x3 we will write x4 plus 1. So it will become 11x4 plus 11. Similarly, in the first constraint, it will be 4x1 plus 6x2 as it is. And instead of 7x3, we will write 7 in the bracket x3 plus 1. So it will become 7x4 plus 7. Similarly, in the second constraint, we will replace x3 by x4 plus 1. And also in the third constraint, we will replace x3 by x4 plus 1 and we get this type of problem. Now we can see that the non-negativity constraints x1, x2 and x4 all are greater than or equal to 0. So this has solved the problem of lower bound, but it has created another problem. And the problem is we have this constant 11 in the objective function, which we have not seen up till now. And we also have these constants 7, 5 and 2 in the constraints. How do we resolve this? So what will we do? We will take this 11 on the left hand side and we get z minus 11. And now we do not have any constant in the objective function and it will look like this. Z dash equal to z minus 11 equal to 10x1 plus 6x2 plus 11x4. And this z minus 11 will be replaced by z dash. So we have new objective function maximize z dash is equal to 10x1 plus 6x2 plus 11x4. And the constant 7 is taken on the right hand side of inequality, 5 is taken on the right hand side of the inequality, and 2 is also taken in the right hand side of the inequality, and we get 210 minus 7, 190 minus 5, and 175 minus 2 to get 203, 185, and 173 respectively. Now, this is a problem which we can solve easily because there is no lower bound. X1, x2, and x4 all are greater than or equal to 0, and there is no constant term. Now, converting this problem into standard problem means a problem where we have equal to sign only instead of inequality. So since all the three inequality are less than or equal to type, we have to add slack variables. So we'll add slack variable S1, S2, and S3 respectively in the first, second, and third constraint. And we'll also add S1, S2, and S3 with 0 as its coefficient in the objective function. Further, we will add S1, S2, S3, all are greater than or equal to 0 in the non-negativity restriction. Now, first we will find the initial basic feasible solution. So putting x1, x2 and x4 equal to 0, that is x1, x2 and x4 as non-basic variable, we get S1 equal to 203 from the first constraint, S2 is equal to 185 from the second constraint, and S3 is equal to 173 from the third constraint. Thus, S1, S2 and S3 becomes the basic variable which will come in the solution. So the table looks like this. S1, S2 and S3 are the basic variables whose coefficients are 0. Then x1, x2 and x4 has coefficient as 10, 6 and 4, 11 respectively in the objective function. And S1, S2, S3 have coefficient as 0 in the objective function. And we will write the coefficient matrix, the identity matrix, and what will be the next step? To find correct ZJ value and then Cj minus Zj value. So how do you find ZJ value? For this place, we'll find the ZJ value this way. 0 into 4. So 0 is here, 4 is here, 0 into 4 plus this 0 into 0, 9, 9, 0 into 9 plus this 0 into this 0. And we get it as 0. One more explanation. 6 into 0, 6 into 0, 1 into 0, that is 1 into 0, and 13 into 0, that is 13 into 0 is 0. Now, we have all Zj value as 0 and the Cj minus Zj value are like this. Now, since S1, S2, S3, all three are in the solution, their entry under Cj minus Zj should be equal to 0, and which is 0. Now, the next step is to find the variable that will enter in the basic, that is the maximization sum. So, maximum value under Cj minus Zj, that is 11. So, this x4 becomes the key column and x4 will now enter the solution. And who will leave the solution? How do we find that? Yes, you guessed it right. We divide the solution column values by the key column values and we get a ratio as 29, 37 and 86, out of which 29 is the minimum value. So this row which belongs to S1 will leave the solution and the intersection of key row and key column is key element, that is 7 in this case. Or next step would be to make this 7 as 1, 5 as 0 and 2 as 0, which can be done like this. So here we have made 7 as 1 by performing this row operation, that is R1 new equal to R1 old divided by 7. Then to make this 5 as 0, we perform the row operation R2 new equal to R2 old minus 5 into R1 new. And similarly to make this value of 2 equal to 0, we will perform the operation R3 new equal to R3 old minus 2 into R1 new. And these values which we have found out now will form the first iteration. We have written it in the new table and we found the Zj value. Next, we will find the Cj minus Zj value as it is shown. And we can see that x4, s2 and s3 which are there in the solution have 0 as the Cj minus Zj value. Then minus 11 by 7 is negative, so S1 cannot enter the solution. X2 is minus 24 by 7, which also cannot enter the solution because this is the maximization problem and this value is negative. So the only variable that can enter the solution is X1. So this column becomes the key column. Next step is to find the key row or the outgoing variable. How do we find it? We divide the solution values by key column values and we get this is negative, so forget about this. And the least value is 6.51, which belongs to S2. So the variable S2 will leave the solution and variable X1 will now enter the solution. And in order to do that, we have to make 43 by 7 as 1, 4 by 7 as 0, and minus 8 by 7 as 0. And we get it like this. R2 equal to R2 old into 7 by 43. Then R1 new equal to R1 old minus 4 by 7 into R2 new. And R3 new equal to R3 old plus 8 by 7 into R2 new. So this forms the table for iteration number 2. And we again find the value of Zj and Cj minus Zj. And we see here that all the entries under Cj minus Zj are either 0 or negative. It means we have reached the optimal solution and the iteration stops here. Now from this table, we get x4 is equal to 1087 by 43, x1 equal to 280 by 43, s3 is equal to 5265 by 43, and x2 is equal to 0, and s1 and s2 are also equal to 0 since they are not the part of the solution. So from this, we can get the value of x3 as x3 is equal to x4 plus 1, which is 1130 divided by 43. Now z dash is equal to z minus 11. This we have converted at the start of the problem. So z will be equal to z dash plus 11. So z is equal to z dash, which can be obtained by substituting the value of x4 and x1 in this equation, where x2 is equal to 0. We get z is equal to z dash plus 11, that is equal to 354. Thanks for watching. If you have understood and liked the video, please hit like button and subscribe to my channel. Thank you.